Okay, this is Navika Academy, and we want to look at group. This is a topic we are discussing group theory 1, undergraduate level, and we want to know the definition of a group. So group, we said group is from a previous discussion. We said that there are two key things that we need to identify. First, we need to know the definition of semi-group, and we want also to know the definition of group point. And group point introduced to us one thing here, which was actually that group point test closure in an algebraic structure, and semi-group looks at associativity property in any given algebraic structure. We mentioned also an algebraic structure is a combination of these duo, and given non-empty set G, defined against and given binary operation star. So if this algebraic structure is satisfies closure property, then that is a group point. And if it satisfies semi-group, associativity, then that becomes a semi-group. Now today we want to see how the group now is defined. And we find that a group is also an algebraic structure. It's also an algebraic structure. And this algebraic structure, in addition to being a group point and also a semi-group, so that means being closed and associativity, and group adds to other additional properties. That is identity, and number 3 of next, inverse. Therefore, a group is a group point. Secondly, is a semi-group, and thirdly, as identity and its inverse. This means for closure, there is for G1, G2 in the given non-empty set G, then G1, G2 will be in the G. That's a closure property. Secondly, associativity tells us that for G1, G2, G3 in G, then G1, G2, G3 will be same as G1, G2, G3. Okay, G3. So that next identity. So for identity, we see that there exists an identity element E, such that for G in G, okay, for an element in this non-empty set G, there exists G will be same as E G, which is equal to G. Fourthly, Fourthly, inverse. This tells us that every element in G, okay, has an inverse. Mark this. Every element in G has an inverse. Okay, so that for all G in G, okay, then there exists an inverse of G in G, such that, okay, if you do this, whichever way, okay, whichever way, you'll get identity. So if you see, you find that we have an algebraic structure which all these four properties owned or axioms owned, then we say independently that is a group. If we may look at some examples of groups that we know in our field, is that we have this group of integers and a binary operation addition. If you test these axioms, you see that they will hold. Another one is the rational group and addition. A rational set and addition, real sets and addition still, and also complex group set and addition. Those are the key groups that are commonly used or we normally interact with. Obvious in these cases here, the identity, if we may look at identity for each, we'll find that the identity for this is actually the 0. And if we may mention about the inverse will be actually the negative x. So this negative x will be the inverse of an element x. Okay. Another common group that we interact with here, you can take as an example, is actually the natural number group and addition. It's also a group. Sorry, can it be a group really? There's something should be not be working properly for this, because I don't think that national group is rightly to get the inverse in the same group from the idea of closure. So that means this will be act as a good example. This is a good example of a non-group. So if you just think about a non-group, a national group and addition will make a good example, because you'll not be able to get if you get a m, then its inverse, which is actually negative m, is not in the natural set. So closure, and by definition of that, that's it owned. Okay. Let's look at matrix also. If you look at matrix and real, you find that if we do this and addition, you find that this is a group. It is a group because if 0, 0, this matrix with all zeros, it becomes the identity. So this is identity. It's identity. And again, we know the inverse. The inverse will be itself the negative. So if you have a given B, matrix B, then the negative for B, the matrix negative B, is actually the inverse of that. That's by true. It's a fact. It's a fact. That's a fact. So we note that. Then we can have more examples. More examples. Let's have more examples. Another example is under multiplication. Suppose we have mn under multiplication. Do you think this will be a group? Don't think so. But it can be a group by under one condition, that the determinant of this group, determinant of this matrix here is not 0. Because if it becomes a 0, then we will not be able to get the inverse. We will not be able to get the inverse. And that means that it will not be a group. It will not be a group. But if we can get all matrices which are none, the determinants are not 0, then it means that we'll be able to get the group. We'll be able to get the group. So to that extent, if you have not yet subscribed to this channel, kindly subscribe. And we have said this is Ndavika Academy. If you have a question on either of these topics, you can just leave as a comment down there, and remember to share with your friends. And if your comments, we'll be able to look at them and work on them.